Hi, everyone. In today's lesson, we're going to talk more about motion. So we did a lot of the basic stuff yesterday. So today we're going to talk more about some definitions. We know that a particle is at rest when the velocity is zero. And we know that a particle changes direction when our v of t equals zero and there's a sign change. A particle will move left and right according to when v of t is greater than zero, it'll move right. So that greater than zero means positive. And a particle will move left when v of t is less than zero. That means negative. A particle will speed up when v of t and a of t have the same signs. A particle will slow down when v of t and a of t have opposite signs. And if I want to know instantaneous speed or speed at any time t, that's equal to the absolute value of v of t. Okay, so let's talk about this through an example. So we have a particle moving along an x-axis according to the standard position function, where x of t is measured in centimeters and t is measured in minutes. So when does the particle change direction? Well, we know that it has to change direction when v of t equals zero and there's a sign change. So let's first find v of t. V of t is the derivative of x of t. So I'm just going to do a quick power rule. So 6t squared minus 30t plus 24. So I'm going to do exactly what it says. I'm going to set v of t equal to 0 and solve. So 0 equals, looks like I can take out a GCF of 6. So t squared minus 5t plus 4. I'm just going to do a quick add multiply. And those factors would be -4 and -1. So I'll do a t-chart here, t equals 4 and t equals 1. This 6 equaling 0 we can reject, it makes no sense. So we've got two possible values where the particle would change direction. In order to verify if it changes direction here, we have to do what we call a number line to test and see if it does. So that's why it also asks when will the particle move left or right. So we said from up here, the particle will move left and right when I have positive velocity or negative velocity. So this is what I'm talking about when I say a number line. So we're going to draw in a v of t number line, and it's very important that we label it so that we know what we're talking about. And the number line, we need to start at 0. And the reason why we started at 0 is because time can't be negative. It says time must be greater than or equal to 0. So we'll always start it at 0. And we're going to put these two values that we got here, the 4 and the 1, and we're going to put them here on our number line. So we have 1 that would probably come first, and then 4. And what we want to do is we want to test values into my v of t function. So my v of t function was this function that we just got. And we want to pick values, so I'll highlight this as well. We want to pick a value that's between 0 and 1. And then we want to pick a value that's between 1 and 4, and a value that's greater than 4, and test it into this function. And all I care about is if the function is positive or negative, right? Because I'm looking to see positives and negatives. I don't care what the value itself is. So you can test any value that you want. So I'm just going to put here, I'm going to test 0.5. Here, I'm going to test 2. And here, I'm going to test 5. Again, any value in between works. Those are the values that I'm going to test. Now, you could go ahead and put 0.5 in for every value of t and see what happens. Same thing with the 2, same thing with the 5. Or we could use the calculator to help us. So what I would prefer that you do is go into your y1 and put in 6t squared minus 30t plus 24. So take a minute, pause the video, type that in, and then look at the table. Okay, so when you typed it in and looked at the table, I want you to look at what's happening at x equals 2 and x equals 5. We don't know what's happening at 0.5 because our tables aren't set up for that. But at x equals 2, you should see that it's a negative value. And at time equals 5, you should see that it's a positive value. So between 1 and 4, since that's where 2 was, I could put in negatives. And between 4 and bigger, I could put positives. Now, some of you might be wondering, well, how can I get that 0.5? And you absolutely can if you play with your window or your table. So you want to hit second table set, TBLSET. It's on the top in the gray areas. And then you're going to do your table start. It should say TBL start. You're going to start at 0, and then it should say triangle table. That's delta, so your change in table should go by 0.5. And then if you look at your table again, so go back to your table, you should see at 0.5 now what the value is, and that should tell you that it's positive. So positives here. So do you see how it went from positive to positive at 1 and 4? There were sign changes between both. So to answer this question, when does the particle change direction? So the particle changes direction at time equals 1 and time equals 4. Now second, when does the particle move right? And when does the particle move left? So the particle moves right when our velocity function is positive. So it moves right from 0 to 1. That's where it's positive. And we could put a little union symbol for another one. It's also positive from 4 to infinity. And the particle moves left when our velocity function is negative. So 1 to 4. And this is just interval notation, right? The parentheses mean that. Okay, the last part is when does the particle speed up or slow down? So that happens when v of t and a of t have the same signs for speeding up, and slowing down when v of t and a of t have opposite signs. So we have to first, step 1, find a of t and set that equal to 0. What we're going to do is make a v of t number line and an a of t number line. So the a of t, we know, is the derivative of v of t. So we're going to take the derivative of this and call that my a of t function. So I'm just doing a quick power rule. So 12t minus 30. And we want to set a of t equal to 0, just like we did with v of t. So we'll add the 30 to both sides and divide the 12. And this, I think, works out nicely to 2.5. So we'll say 2.5 equals t. So what we need to do with this one is we need to make an a of t number line, just like we did before, a of t. Notice that I'm putting it down here. The reason why is because we are going to copy our v of t number line from above below here. So I might as well do that now. So this was pluses, minuses, and pluses. And now our a of t number line at 2.5 is where the acceleration is 0. So notice where I'm going to put the 2.5. I'm going to put it between the 1 and the 4. So right in here, 2.5. So we need to test into our a of t function this time. So a of t, and we need to test the value. Again, time can't be bigger than less than 0, so we need to make sure that this starts here at 0. So pick a value between 0 and 2.5 and a value that's bigger than 2.5 and plug it into your a of t and see what happens. So again, pause the video, put this into your y1 and look at the table. I would say a good test value here would be 1. So time equals 1. Here, a good test value would be 3 or 4. Anything works. So take a couple seconds, go to the y equals, put this in, and look at your table and see where it's positive or negative. And then hit resume when you're ready to do that. Okay, so I got that when x was 1, that this value was negative, and it's positive here. Okay, so the goal is to figure out speeding up and slowing down. So a particle speeds up, we could put this here, so speed up, when the signs are the same. So the easiest way to do this is to kind of break it up to where like these values are on the number line. So break it up here, break it up here, break it here, and then it's clear to see. So I'm going to use the highlighter here. I'll use yellow. We're going to highlight. Where are the signs the same? They're the same here. That's not the highlighter. Let's use this one. They're the same here and here. And they're the same here and here. So those would be where it speeds up, where the signs are the same. So speeding up from 1 to 2.5. So we can say 1 to 2.5. Union, there's another one, from 4 on. So 4 to infinity. And it slows down where the signs are opposite. So let's highlight that. So the signs are opposite here and here and here and here. So we can say from 0 to 1 is where it slows down. Union from 2.5 to 4, opposite signs. So 2.5 to 4. So if you take a look here, it changed direction at 1 and 4. So let's go. Okay, let's jump to this back page now. What is the particle's total displacement over the interval from 0 to 3? So remember, displacement, there's a formula for that. It's x of b minus x of a. And remember, a and b are the endpoints of the interval. A is the beginning, b is the end. So x of 3 minus x of 0. So we need to go into our x of function, or our standard position function, and find these values. So it would be helpful if we know what our standard position function is. So I'm just going to rewrite this here on the top here. So my standard position, x of t, I'm just reading it from the top of the front page, 2t to the third minus 15t squared plus 24t plus 8. So all I'm going to do is take a page out of the book that we did before. We're going to put this into our y1, and I want to find out what x of 3 is. So go ahead, pause the video, type this into your y1, figure out what x of 3 is, figure out what x of 0 is, and subtract them. And then hit resume when you're ready for the answers. Okay, so x of 3, you should have gotten -1. And x of 0, you should have gotten 8. So -1 minus 8 is -9. So a displacement of -9 means the particle ended nine units to the left of where it started. And then the particle's total distance, if we remember from yesterday, we had to draw a picture of the scenario in order to do that. And distance comes from where it's positioned on the line. So we need to know a couple things. We have an endpoint, A and B. So I'm going to draw a little table. So we have X, or time rather, I'm going to put T. So we have T and X of T. And I want to know over the interval of 0 to 3. And you're going to notice I left some space. Why? Because yesterday when we added up all the segments, we encountered for where it changed direction. So we actually have to go back to the front and see where it changed direction. And obviously 4 is out of the interval, so the only one that we can put in here is 1. So what you're going to do now is, since this is still in your y equals, go back to your table and tell me what those y values should be. And we found 2 of them already. At 0, it was 8, and at 3, it was -1. So -1 here, 8 here. So you just need to tell me what's happening at 1. So if you looked, it should be 19. So let's draw a picture of this. These x of t values, these 3, are your standard positions. These are your locations. So we are located at, we could put -1 here, we could put 8 here, and we could put 19 here. The number line doesn't have to be perfect, but I do have to say at time equals 0, I'm at 8. At time equals 1, I've traveled to 19. And at time equals 3, I traveled back to -1. So we know from yesterday, all we need to do is add up all of the values, and then that will give us our distance. So from time equals 0 to time equals 1, I've traveled from 8 to 19, which is a total of 11 units. And we know from time equals 1 to time equals 3, I've traveled from 19 to -1, which is a total of 20 units. So we add 20 plus 11. That gives me 31 total units for my distance. And that's it. That is how we do particle motion with an equation. All right, try to see if you can try example number 2 on your own. I know it's a graph, but it's the same kind of concept, and we will definitely start class tomorrow by going over this. All right, have a good night.